What up, peeps? We're back here to talk a little bit more chemistry. We're going to talk today about covalent bonding and lead our way to covalent compounds. So along those lines, I wanted to just remind you of a couple of things, that everything that we're going to see all happens because we're trying to satisfy the octet rule to become quote-unquote isoelectronic with noble gases. So in a sense, elements are kind of fooling themselves into thinking that they're noble gases, but you know, they'll never live up. So let's imagine just that we're chlorines to start off with. It's a really convenient kind of starting point. And what we're going to do is we're going to recognize that an uncharged chlorine has 7 valence electrons, as you might expect from the periodic table. And we're also going to represent that in a Lewis structure. It turns out that talking about these kind of bonding situations is made much easier if we start to kind of keep track of those valence electrons. So what I'm going to do is I'm going to imagine all of the electrons that I as a chlorine have floating around me. And you'll notice that I have exactly 7 valence electrons. And you might expect that I would be very, very unhappy. And it turns out a chlorine, neutrally charged, hanging out, is incredibly reactive because it is so incredibly unhappy, and it is so close to getting to that octet. So of course, if I had somebody that I could beat on, like a metal around, I could just rip an electron off of that metal, and I'd be at Cl minus, and I'd be all happy. But the problem is that some people can fight back a little bit and kind of hold on to their electrons. And so you got to come up with a little bit of a sneakier way to satisfy your octet. And so what we're going to do is we're going to pretend that we're some sort of chlorine here, and we recognize that I have my 7 valence electrons. And then we're going to imagine that maybe our neighbor is a hydrogen. And you'll remember that a hydrogen is in the very first column of the periodic table, which means that it has 1 valence electron. And I'm going to represent that as an X, right? And so it's just, instead of a dot, I used an X so that you can kind of keep track of where that electron came from. So what we're going to do is we're going to recognize, well, hydrogen is looking for another electron, right? It turns out that hydrogen, much like helium, is an exception to this octet rule. Turns out as long as it fills its principal shell, the outermost principal shell, which in hydrogen, you don't get much more simple than that, turns out that you satisfy the octet rule by having 2 electrons, and that's kind of a weird thing to say. So as I mentioned in another lecture, like the octet rule is kind of a bad name. It really should be the full principal shell rule or something like that. Or, you know, I don't know what to call it. But so anyway, if our neighbor hydrogen here is unhappy and in search of 1 electron, and chlorine is unhappy in search of 1 electron, you could imagine that these two would kind of come close together, and as they approached one another, you could imagine chlorine thinking, oh man, I'm not really doing much with this 1 electron. Maybe I'll just kind of share it with a hydrogen. And hydrogen does the same, says, oh, I've got this 1 electron, I need another electron. And so what we're going to do is we're going to have this kind of area in between each other here. So there's my chlorine nucleus and my hydrogen nucleus, and they are going to hang out together. What we've just represented is what's known as a single covalent bond, right? So this guy right here, this is a single covalent bond. You'll notice that that bond actually involves 2 valence electrons. That's one thing that's really important that you know, is that every time you see a bond, that it involves 2 electrons. And the problem is that most of the time in a Lewis structure, you don't represent a bond like that. What you do instead is you actually draw a line between these 2 elements. And so this guy right here, that is also a single covalent bond, and quite honestly, it's probably the slightly more common way of seeing covalent bonds. And one of the things that you'll notice is that you've created a molecule now, right? That idea that you need to kind of have this tightly packed unit, right? The hydrogen can't just go about its own business. It has to always carry around a chlorine, and chlorine always has to carry around a hydrogen because they're in rainbow and unicorn land kind of sharing their electrons. And that is something that's not true of ionic compounds. Ionic compounds can kind of split apart into their positive and negative charges and then come back together. We'll talk about solution chemistry at some point, and you'll notice some big differences between what covalents can do and what ionics can do. So that's a single covalent bond. As you might expect from the fact I called it a single covalent bond, there are other kinds of covalent bonds like doubles and triples and things like that. But before we get to that, I did want to mention just kind of another example of what chlorine could do, right? So here we've satisfied all of our octets. We've got a molecule, by the way, this is hydrochloric acid, also known as muriatic acid. Super fun stuff to play with, really strong acid. So anyway, let's look at this chlorine again. But this time, let's imagine that that chlorine doesn't have a choice to bond to a different element. What if I put another chlorine over here? And these are both unhappy, right? And so these also might come together, and they do, and to form a molecule. And what you're seeing before you is this example of a diatomic element. We talked about in one of the very first video lectures this idea that there are some elements that can't exist alone. This is part of the reason that chlorine can't exist alone, is that it's super duper reactive and unhappy. So the second that it exists alone, it kind of needs a buddy, right? They're kind of twins. And so these guys are going to have to exist together in this happy environment here. I should mention that, like, oftentimes it's not important that you keep track of what electrons kind of belong to what. So I'm just gonna, you know, kind of let's do this first, just so you can see that the situation is no different. Right? I still have a single covalent bond that I could represent that way without just drawing a line. Doesn't matter which way you do it. But the problem is that once you start to talk about valence electrons, sometimes it's not advantageous to kind of say like, well, you started with this many valence electrons and these are yours, and these other ones are somebody else's. So it's kind of like you know, the people that you go to a party with, right? You hang out, you go to the raging party with, let's say, 4 different friends, and you probably lose track of your friends at some point, but they're going to be pretty happy away from you. You might see another one at some point. So in much the same way, valence electrons, they you want to count the numbers at the beginning when they come to the party, right? And then once you get to the party, they all kind of just do their own thing, whatever is kind of convenient for them. I had to edit out an inappropriate comment I made about an ex-girlfriend. So what we're going to do now is we're just going to represent every electron with a dot here. And this is probably the much more common way that you'll see this written. So here's my diatomic chlorine with all the dots. And so if you see life as this chlorine, I see a total around me of 1, 2, 3, 4, 5, 6, 7, 8 electrons, right? And I'm said to have satisfied my octet right there. Turns out this guy over here, which I'll do in blue, this guy has also satisfied his octet. What you'll start to kind of notice is that these spheres that I'm coloring here, you'll recognize those from the particle diagram of matter. Right? And so this is the reason that those 2 diatomic spheres had to stick together, right? They actually had a bond in between them that was being shared. Okay, so you might notice I changed the name up here to bonding, because technically when we were just looking at that Cl2 molecule, technically that wasn't a compound, right? So I erased compound and I just put bonding. That was actually an element, but we all know that already. Wow, there's a dog party upstairs. I hope you can hear that. My goodness gracious. That's a lot of barking. I probably should go check, but I'm sure everything's fine. I'm sure they're not eating all of the bacon in the refrigerator. Okay, let's imagine now that we're in oxygen. You know that oxygen is in the 6th column over, meaning that that has 6 valence electrons in its uncharged state. So drawing a Lewis structure of that might look something like this. If this has another oxygen around, these will both be unsatisfied, but let's take these two atoms and we'll bring them together just like we brought together the chlorine nuclei, and let's see what happens. And you'll notice that if you look at the total number of electrons around each one of those, I'll just darken these a little bit so you can see them a little better in the video. You'll notice that we're close, right? We've got 7 now, we had 6 before. And so the key here is to recognize that these two electrons aren't really doing anything out here. So I'm going to erase those and put them in between the 2 oxygen atoms. It turns out what we've done here, this is a Lewis structure representation of what's called a double covalent bond. You'll notice that a double bond shares a total of 4 electrons now. Another way that we could have written that, the more common way of seeing this thing known as diatomic oxygen, looks like this. And so you'll notice this oxygen is seeing 8 electrons, that oxygen is seeing 8 electrons. And as you'd expect, that double bond is slightly stronger than the single bond that we saw before between the 2 chlorines. It's not twice as strong for some reasons we'll probably never get to, but it is a much stronger bond situation. And you're kind of happy about this because every time that you opened up like a can of gas, for instance, if this bond wasn't relatively stable, you'd probably explode. Bad day at the office. There are important things about understanding these different bonding theories in terms of real life. One of the important things that I should probably mention is that you could, have really any number of bonds as long as you get to that satisfied octet, but typically we're only going to see single, double, and triple bonds. A great example of a triple bond is the case of nitrogen, which actually looks like this. And you'll notice that that triple bond is, well, first of all, I didn't draw it very straight. Sorry about that. I was just a little googly-eyed. This nitrogen, a really strong triple bond. One of the reasons that this is important to us, especially as biological beings, is that we need nitrogens. And the problem is that even though the air is like 70% nitrogen, it's all tied up in this really strong bond. So there are these little bugs called nitrogen fixing bacteria that can actually split this bond apart. But, it's like something that requires a ton of trickery or a lot of energy. We, as, in the 18th, it's mostly in I think the late 18th and early 19th century, came up with something called the Haber process. That's pretty much the #1 user of the world's energy supply, is just to break this sucker apart into like individual nitrogens that we can then incorporate in some way into biological systems, or also explosions like munitions and things like that, the nitrates in exploding things like gunpowder and such. So these nitrogens are really important, and this idea of a triple bond, sharing, by the way, 6 electrons total, is a really strong kind of bond. As we kind of go on with covalent bonding, we'll see all kinds of different Lewis structures, some of which we saw in one of the previous video lectures. But just to kind of show you an example, is you can have bonds that look like this, right? A bonding situation where you'll notice that carbon has now satisfied its octet, but it's bonded to a whole bunch of different elements, right? And so what we're building with this covalent theory is like gradually building the size of our molecules. And what the next couple of video lectures are going to have everything to do with, it's going to be taking pictures like this that I mostly give to you. There are techniques for drawing Lewis structures for these things, but I'm already overwhelming you with the amount of information I'm throwing at you in a small amount of time. So I kind of cut that out. And I will say is that I will give you the Lewis structure of anything that's more complex than just, you know, a simple diatomic or something like that. But the cool thing is once you have this, you actually know what the picture of the molecule looks like, right? And that's called VSEPR theory that the next video lecture is going to address. So we'll kind of leave it there. You should recognize that this oxygen still sees its 8 electrons. And one kind of like important thing to recognize in Lewis structures is the once that hydrogen bonds once, it's all done. It's satisfied its octet. It's got its 2 electrons. So that's kind of a, you know, that's an important thing to know as we progress here.